I did fail to bring my QR code with me, so you'll just have to sign into class another way. I'm sure you're all capable of doing. We'll get going in just a minute here. Get from here. Hence. So in case it wasn't clear, we're going to review for the exam students in the Dell's class have tomorrow. Number of things we have to cover. I just wanted to point out, just so you have all seen it, for those of you in his class, let me go ahead and pull up his Canvas page real quickly here. Not my Canvas page. Yeah, okay. So you all can see this here. Look at the announcements specifically. There are two you should have seen for sure. Specifically, the one about midterm 3 handout and lesson matrices, and also the one about test 3. If you look at the test 3 one, talks about what you're covering, and then the usual kind of rules, whatever. Actually, maybe the test 3 one wasn't so much, I guess, what you're covering. The other one here about the handout is talking, gosh, I can't read this very well from over here. Are those what they want to look at? Yeah. Posted a handout. Maybe it was an email he sent. Now I'm like, because I feel like he very specifically laid out which problems you should not focus on. Yeah, but I'm not seeing, why am I not? Okay, thanks. Yeah, so there were two things. He talks about discussion sheet 9 and how you shouldn't focus on the practice problems. So, yeah, here it is. So for discussion sheet 9, essentially don't look at problems 2 through 7, because those are for the final. And then for the practice problems, which is different than discussion sheet 9, these problems 1, 4, 7 through 10, 11, 13, 15, 23, 27, final. So just when you're looking at these practice problems, those ones you should hold off on. Not that we couldn't talk about those if you really, really, really wanted to, but I feel like there are other things we are more pressing. So if you're looking for what you should and shouldn't look at on your practice materials, I would say that's where you should be looking. All right, so let's take a little bit of time to talk about Leslie matrices, because I know that that's something that was talked about in class yesterday, and it always feels a little challenging. They're not that bad. So let's look at this problem, which I will try my best to write up relatively quickly here. So let's say we've got the following. Consider a population of women, I don't really want to write all these words, at risk of developing breast cancer. I know, what a light topic, but these are the biology examples we have. And so let me just break down what we've got here. There are 3 states. You have 1, healthy, 2, early stage disease, and 3, late stage. And here are the important numbers. Each year, 0.3% of healthy women develop early stage, with their rest remaining healthy. 68% of early recover. Can you read this correctly here? And 32% of early. Sorry, I'm having trouble. 68 of early recover, and 32% develop late stage. And finally, 15% of women with late stage revert to early, and the rest remain in late stage. 85% remain in late. We're going to use H, E, and L to denote the number of individuals in each state. So H sub T is the percent that are healthy. E sub T is the percent that are early stage. And L sub T is the percent that are late stage. So let's draw the Leslie matrix diagram to represent this. So we have 3 stages, which we're going to represent with 3 circles. Got your healthy, early, and your late. So reading through this, we see that 0.3%, so 0.003, yeah, 0.003, right, 0.3% of healthy develop early. So 0.003% of these, sorry, not 0.003, sorry, I'm saying words wrong. 0.003 of those healthy individuals will develop early stage. 68% of early recover back to healthy. So from early to healthy is 0.68. 32% of early develop late. So 32% of the earlies, or 0.32, become late. 15% of women with late revert to early. So from late to early is 15%. And finally, the rest of the women who are late stay late. So 85% of the lates stay as late. Now, there's something missing from all the things I've said. 0.003 of the healthy develop early. Sorry, 0.3% or 0.003 of the healthy go to early. What about the rest of them? Well, they stay healthy. So the other 99.7% or 0.997 of the healthy stay healthy. That's not always something you have to worry about, where making sure that 100% of the stuff goes out or stays in. But in this context, we do have to kind of think about that. Great. So here's the diagram, which isn't too terrible. Now we're going to write the Leslie matrix. And it's actually not that bad once you figure out what's going on. It took me a while, I'm not going to lie. Like, I was always like, this work. But here's the way to think about it. The Leslie matrix, hope you all can see that. Sorry, let me turn in frame here. So the Leslie matrix is going to look like this. So you have this matrix multiplied by the healthy, the early, and the late at some time is going to give you essentially the next time iteration of the healthy, the early, and the late. Here's the easiest way I have found to think about it. All the things that are going into the healthy, or whatever the first one is, should be in your first row. So my first row, I should have 0.997 for healthy and 0.003 for early and 0 for late. So 99.7% of the healthy people stay healthy, 0.3% of healthy people become early stage, and 0% of healthy people become late stage. That multiplies that, that multiplies that, that multiplies that. And then we do the same thing for the other two. So what's going into the early? Well, I'm sorry. Brain. Oh my gosh. Brain. I said the wrong thing. Now I was like, it's gonna be this. No, I apologize. I said the wrong thing. Killing me, James. Oh, I said the right thing. I wrote the wrong thing. This first row should be the stuff that's going into the healthy. Apologies. So it should be 0.997 times the healthy, and then going into the healthy is 68% of the early and 0% of the late. So let me say it again with more conviction. In this first row should be all the things that are pointing into the healthy, or whatever the first category is. Similarly, in this second row should be all the things going into the second category. So I should have 0.003 of the healthy. None of the early actually stay early, right? There's no arrow pointing back into itself. And 15% of the late. Thirdly, all the things going into the late are 32%. So I should say none of the healthy, 32% of the early, and 85% of the late. And that is what our Leslie matrix should look like. So the way I like to imagine things here is that each row is what's going into the first category, into the second category, into the third category. And similarly, each column is what's coming out of that category. So the first column is what's coming out of the first category. The second column is what's coming out of the second category. And the third column is what's coming out of the third category. That's how I really think it makes the most sense to imagine this. So then you could ask a question like, what percentage of people are going to have, be healthy early, late in 2 or 3 iterations, which just means you're doing multiple matrix multiplication. Now, if we call this matrix, let's say this is A, if we said, what percentages, sorry, will we have in 3 years, given some initial values? We're not going to make a calculation here. H naught, E naught, and L naught. It would be the matrix A cubed times R H naught, E naught, L naught. This is just to point out that the whole idea here is that you're not trying to do this calculation like by hand every time. You're trying to say that it's just repeated matrix multiplication. But again, I'm not focusing too much here on the actual multiplying matrices for this particular problem. So let's do one more thing with this. So I want you all to try your hand at the following. So here's a diagram. A is the first category, B is the second category, C is the third category, and here are the numbers we have. We have 4 times C going into A, we have 1 of A going into B, we have 2 of B going into itself, and we have 3 of B going into C. I want you all to try and draw the 3 by 3 Leslie matrix for this diagram. And I'll give you another diagram to do. If you finish that one, here's another one for you. That's a little messy looking. Okay, so this first one here, what's going into A? Well, A is not going to itself. B is not going to A. In fact, the only thing going into A is C. So 0A is going into A, 0B is going into A, 4C is going into A. What's going into B? Well, A, B, so 1A is going into B, 2B is going into B, 0C is going into B. What's going into C? Looks like just 3B. So 0A, 3B, 0C. And then the thought here is that if you took this matrix and you multiplied it by the quantities that were in A, B, and C, you would get next iteration's quantities that were in A, B, and C. So for example, if we start with, and again, we're just kind of making things up here, you know, A equal to 100, B equal to 20, C equal to 10, then the next iteration is going to have this matrix 0, 0, 4, 1, 2, 0, 0, 3, 0 multiplied by 100, 20, 10. Sorry, I multiplied. No, that's fine. So then we just do the matrix multiplication. So this first row dotted with this first column is going to be 0 times 100 plus 0 times 20 plus 4 times 10. And then this second row dotted with this first column is 1 times 100 plus 2 times 20 plus 0 times 10. And then this third row dotted with this column is 0 times 100 plus 3 times 20 plus 0 times 10. So after one iteration, you're going to have 40 in A, 140 in B, and 60 in C. And you can keep doing that if we were asked to. And later on, next week, we'll talk about how you do this a lot of times with an easier calculation. Easier might not be the right word there, but a different calculation. So for this other diagram here, let's draw the matrix as well. Draw is not the right word. Let's write the matrix. So for this second diagram, again, I'm really just trying to see what's going in and out. So I need 4 rows and 4 columns. So into A, I have 1 of A, nothing else. 0 of B, 0 of C, 0 of D. Into B, I have 3A, 6B. C is not going into B, but D is. So 0C, 5D. Into C, we have 4A, 2B, or not to be. Ha ha ha, I know, yeah. No C itself, and 8D. And finally, going into D, the only thing going into D is D itself. So 0A, 0B, 0C, 2D. That's how we would write the Leslie matrix for that. So hopefully that gives you a relatively fast way of knowing how to write the Leslie matrix based on this picture here. Question? These values right here, I made them up. Yeah. So typically, if you're asked to like actually find, like if you're given like the initial population is this, this, and this, and then you're asked like how many people in each category you're going to have 3 years or time iterations later, you would then multiply that initial column vector or column matrix, whatever you want to call it, by the matrix, the Leslie matrix, 3 times. Not that I think you would be asked to do that. It probably has to do it like once or twice. But that's the idea with the Leslie matrix. It tells you how many you're going to have each further iteration of years, weeks, whatever your time is.
And then you go with like the larger values, the smaller like values. Like let's say if it was given like 5, 4, and 3 years. 5, 4.
So yeah, so I mean, so each so like for example, if this Leslie matrix is representing like how many we have next year, then I want to say how many you have in 5 years. Well, you're gonna have to do this 5 times, but you would say like, so after 1 year would be A times whatever your, let's call it X naught vector is. And then 2 years would be A squared times X naught. So you would do A times the result you had from there. And you would just keep multiplying your result by A again and again and again until you did it enough times. But again, we'll see next week that there's a way of simplifying that calculation, which is still not that simple. Yeah.
So if it was like A cubed times X naught, if we wanted to do A cubed, we would have to do like the A matrix times itself 3 times.
Well, so actually you can kind of go either way. And I would recommend, so actually let's look at this example here, this previous example. So let's say that for this one here, we have, our matrix, let's call it, I'm going to call it D. That's terrible notation, James. D, you don't put an arrow over a matrix. Is that matrix we just found? I should call it L because it's a Leslie matrix, but oh well, I didn't. 0, 0, 4, 1, 2, 0, 0, 3, 0. And our initial population is the matrix 40, 140, 60. But I will tell you, when you have a matrix that's like a 3x1 or a 5x1 or a something by one, we often call it a vector because it's also a vector. Matrices, vectors have a lot in common. So this column vector here, I want to find out like how many we have in 3. So I want to find D cubed times X naught. And the way I would probably think about doing this is D times D times D times X naught. And I'm actually going to do that multiplication first. You can pick any order you want, but it's often easier to do a 3x3 times a 3x1 versus doing a 3x3 times a 3x3 times a 3x3 and then multiplying it by that. So really, you want to pick the order that's easiest. If we were doing it this way, we'd have, okay, so we already did D times X naught once. So now we have the matrix 0, 0, 4, 1, 2, 0, 0, 3, 0. We're going to do it again. 0, 0, 4, 1, 2, 0, 0, 3, 0. And that's going to be multiplied by the 40, 140, 60 that we got from doing it one time already. So there's one multiplication of D times X naught, and then we're going to do that multiplication there. That's going to be, I'm still just going to write this matrix over here, kind of annoyingly. And then multiplying this matrix by this vector, well, 0 times that, 0 times that, 4 times 60. I do find, as I was telling someone the other day, the pointing really helpful, to be honest. Like when you're doing rows of your first matrix dotted with columns of your second matrix, I point this times that times that times that, add together. And then the next row, 1 times 40 plus 2 times 140 plus 0 times doesn't matter. So 40 plus 280 is 320. And then finally, the third row, you can see that the 3 is the only thing that matters. So that 3 gets multiplied by the 140, which is 420. Then we do it one more time. So then this row dotted with this column, 0 times that, 0 times that. 4 times 420 is something, 1680. That with that, 1 times 240 plus 2 times 320 plus 0. So 240 plus 640 is something, 880 plus you. And then finally, 3 times 320 is 960. So that's how I would, if I had to multiply this matrix by this vector 3 times, is by actually multiplying by the vector, not by multiplying the matrix by itself 3 times. It's usually easier that way. No, well, so this was the I called it D. This was the matrix D multiplied with X naught the first time, which I did up here. So I was just trying to save myself a little bit of work. Yeah, good point. There's not a lot else to say about Leslie matrices. Really, this is how we set them up, right? It's always the stuff going in and the stuff going out.
I have a question.
Yeah, go ahead.
Did we just assign D to this matrix or
Sorry, say that one more time.
did we just assign D for this?
Yeah, I just called it D. And that's something that people do a lot with matrices. There's like, I have a matrix, I'm going to call it whatever I want to call it, usually with a capital letter.
Okay,
Sorry,
thank
I'm missing the things in the chat here. Apologies. Yeah. Okay. All right. So the other thing that we should talk about briefly is just systems of linear equations, because those are something that was talked about. And then I'm certainly happy to answer any questions about any of the practice materials he's got here. So let's go ahead and move over here quickly. That's not what I want. There we go. Sorry, 1 second. Where? Sorry, I lost something here. There we go. So I could see him asking you something like, write the equations 2x plus y equal to 7 and x plus 3y equal to 4 as a matrix equation. So it's not that bad. The numbers that are the coefficients of X and Y respectively are the entries in your matrix. So I have a 2 by 2 matrix. I have a 2 here, a 1, and a 3. That 2 by 2 matrix is getting multiplied the variable vector x, y. And it's equal to 7, 4. And if you look at the matrix multiplication, this equation here and this equation here are exactly the same. They mean the same thing. This says 2 times x plus 1 times y equals 7. This says 1 times x plus 3 times y equals 4. Same thing. Now, the way one would typically solve this is by using the inverse matrix, but I don't think that's something that's going to be on your exam tomorrow, right? I think as far as I saw, right, no inverses. That said, it's still not something that's bad to know. So there's an easy way to find the inverse of a 2 by 2 matrix. Here's what it is. So if we call this matrix A inverse is equal to, you change the diagonal entries. The off diagonals, you change the sign. And then we divide by what's called the determinant of the matrix. So over here real quick, the determinant of a 2 by 2 matrix is always nice. It's the product of the diagonals minus the product of the off diagonals. So in this case, the determinant of A is 6 minus 1, which is 5. So A inverse is 1/5 times the matrix 3, -1, -1, 2. You could write it as 3/5, -1/5, -1/5, 2/5, but no one does that. Which good. So to solve this equation, what we do to solve the equation A times the vector X equal to what we typically call the vector B. To solve AX equal to B, you multiply both sides by A inverse. And the reason we do that is because A inverse times A is the identity matrix. Whatever appropriate size matrix, 2 by 2, 3 by 3, 4 by 4, however big it needs to be, that has all ones on the diagonal and zeros everywhere else. Let's actually check and see if that's true. We multiply these matrices together. 1/5 times the matrix 3, -1, -1, 2, multiplied by the matrix 2, 1, 1, 3. Let's do the matrix multiplication first, and then we'll multiply 1/5 at the end. 3 times 2 plus -1 times 1 is going to be 5, 6 minus 1. 3 times 1 plus -1 times 3 is 3 minus 3, which is 0. -2 plus 2 is 0. -1 plus 6 is 5. And oh, look, if you multiply that whole thing by 1/5, you exactly get 1001. What does that mean for us? It means that this matrix here, A inverse times A, is just the identity matrix. And the identity matrix multiplied by any vector or any other matrix is always just going to leave that matrix or vector alone. It's like multiplying by 1. What's 1 times 5? It's 5. The identity matrix times another matrix is just that other matrix. So what this tells us is that the solution X is equal to A inverse, which is the matrix 1/5 times 3, -1, -1, 2, multiplied by whatever that vector B is, 7, 4. So we get 1/5 times 3 times 7 plus -1 times 4, which is 21 minus 4, so 17. And then -7 plus 8 is 1. So the solutions to this equation are X equal to 17/5 and Y equal to 1/5. Yes, there are other ways of solving it, but this is usually the most efficient way of solving it. Now, again, I know that inverse matrices are not on this exam, but it just felt like this was the appropriate moment to say it. Yeah.
So we have to make, multiply the inverse matrix first before the 7/4.
So I guess I'm not, could you say that again?
So when we multiply the inverse to both sides.
Yes.
On the right, it has to go first.
Well, it's not that it's going from, oh, I see what you're saying. Yes. So yes, excellent question. So sorry, I wasn't catching your meaning before. So here I have to multiply both sides of the equation by A inverse on the left side. If I multiplied A times X times A inverse, the X is in between the A times its inverse and they don't touch each other first. So yes, the side that you multiply matrices on is very important. So you're totally correct. We are multiplying both sides of this equation by A inverse on the left side. Exactly. Right. It would be different if you multiply. It actually wouldn't work if you multiply it on the right. And then A inverse times A is the identity. So you just end up with X on the left side and you get A inverse times B. Yeah, good point. Thank you. Other questions about this idea here? Yeah.
Well.
It doesn't have to be out of this. It can be about something else.
I want to talk to you.
Sure.
It's question 5,
So the practice problems. Question 5. Oh, yeah, good. Question 5 was exactly where I wanted to go. Great. Awesome.
Could you go over these?
Sure. I'm going to go over all of it, but yes. So question 5, we're starting off with this matrix. And certainly if you have questions about the practice exam, you're welcome to write them in there. So question 5. So here's the matrix A. We're given 7, 1, -2, -3, 3, 6, 2, 2, 2. And we're first asked to find A minus 5 times I. So if you see I, that means it's the identity matrix, and it's always of whatever size you need it to be. Has to be square, right? Can't be 2 by 3 or 7 by 2 or whatever. But in this case, it has to be 3 by 3. So that's going to equal A, which is again this 7, 1, -2, -3, 3, 6, 2, 2, 2, excuse me. And then we're going to subtract 5 times the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So essentially, all we're really doing here is subtracting 5 from each of the diagonal entries and leaving everything else alone. So what you're going to get here is 7 minus 5 times 1, 1 minus 0, -2 minus 0, -3 minus 0, 3 minus 5 times 1, 6 minus 0, 2 minus 0, 2 minus 0, 2 minus 5. So that's how we deal with the first part. 5 times the identity matrix is just 5, 5, 5 on the diagonal. Let's look at part B. Solve B times X equal to 0. So different matrix. Oh yeah, this one's interesting. We got 1, 1, -2, -3, -3, 6, 2, 2, -4 times. We're trying to find the vector X consisting of the components X1, X2, X3. We want this to equal 0, 0, 0. How do I know the matrix I is 3 by 3? Because otherwise the subtraction doesn't work. So if they're asking you to calculate A minus 5I, the implication is always that I is the right size that it needs to be. So whatever size your identity matrix needs to be so that the either addition, subtraction, or multiplication works, that's what it gets to be. So here, I want to point something out. This matrix multiplication just represents a system of equations. If you do this first row dotted with this column, you get 1x1 plus 1x2 minus 2x3 equal to 0. And then the second row dotted with the thing also. So it's -3x1 minus 3x2 plus 6x3 equal to 0. And finally, 2x1 plus 2x2 minus 4x3 equal to 0. And what I want to point out here is that these 3 equations all represent the same system of solutions. If you take an equation like, say, y equal to 4x plus 1, which is a line, right? Y equals 4x plus 1 is a line. And there's a lot of points on that line, like an infinite number. One of the points is 0, 1. And another point is 2, 9. And there's a lot of other points I could find. But the point, is that if you multiply this equation by any constant, it doesn't change the solutions. If you multiply this whole equation by 3, you would have 3y equal to 12x plus 3. And you know what? 0, 1 is still a point on that line. 2, 9 is still a point on that line. So when you take an equation and multiply it by a constant, it doesn't change the solutions to that equation. And then what I want us to observe is that this second and third equation are just multiples of this first equation. right? If you take this first equation and multiply it entirely by -3, you get that equation. If you multiply this first equation entirely by +2, you get that equation. So these two second equations here don't really matter. If you find a solution to this first equation, like for example, the point 1, 1, 1, it's going to be a solution to that equation and that equation as well. So really this question is just asking us to find, and here's where it's going to be kind of annoying, find all solutions to the equation x1 plus x2 minus 2x3 equal to 0. I don't actually know if you talked about this in class, but it's on the practice and it's a problem he said not to ignore. So here's how you do this. I have one equation and 3 variables. There's an infinite number of solutions. I have a lot more variables than I have. So we basically say the first one here we're going to deal with later. We're going to set x2 equal to, pick your favorite letter, R, it's not really my favorite letter, x3 equal to t, but these are like the standard choices. R, S, T are typical. And then we're going to solve for x1. x1 is equal to negative x2 plus 2x3, but we're going to write it in terms of R and T. So x1 is really equal to negative R plus 2t. I don't know why they do this, to be honest. Like I would just use x2 and x3, but for whatever reason, we have decided that we're just going to say we're going to let these equal other parameters, R, S, and T typically. So then we can say that our solution is x1 equal to negative R plus 2t, x2 equal to R, x3 equal to t, or written as a vector, x1, x2, x3 is equal to negative R plus 2t, RT, and then we like to break it apart into the R's and the T's. Negative R, R0, plus 2t, 0t. And then we like to factor out the R's and the T's. So it looks like this. So this is the general solution to this particular equation. Kind of funky. Yeah. This is problem 5B on the test 3 practice problems.
I'm sorry, could you repeat the last step, like the last part?
Sure. So what I did was I said x2 should be R, or you pick any letter you like. x3 is t, and then we solve for x1 by saying x1 equals negative x2 plus 2x3, and then replacing x2 with R and x3 with t. And then, yeah, I mean, yes, you need to find all this for 5B. So then writing this out, I mean, so I should say, if you're really asked to solve this, you could probably stop here if you really wanted to. This is a solution. I'm just kind of writing in the way that I know is fairly standard. So writing this as a vector, we have that the vector x is equal to this vector, which then we're writing as negative R plus 2t, R, T, and then we're just breaking it up into the R's and T's. Why do we do this? That's a good question. Why do we do this? I guess, you know what? I would say you could stop here. That's where you should stop. There's more we could do, but it's not really necessary. All right, I'm getting to 5D. I know you asked about 5D, so let's get there. Sure. So actually, to do 5D, we should do 5C though, because 5C helps us see what's happening. So find A times X, where X is the vector 1, 1, 1. So A is the matrix 7, 1, -2, -3, 3, 6, 2, 2, 2. X is the vector 1, 1, 1. We multiply this out. So again, it's 7 plus 1 plus -2. It's going to be 8 minus 2 is 6. -3 plus 3 plus 6. 2 plus 2 plus 2. And I will point out that this is exactly equal to 6 times the vector you started with. So that we have that A times X is equal to 6 times the vector X. And this is important to notice because of the next question. So here's what question 5D says. 5D says, find another vector D. I'm going to say a different vector D. It uses a capital. Such that A times D is equal to a constant times D. So here's what we should do. Oh, question.
Did you say?
I didn't choose it. I didn't get to choose. So this was part C, and part C said take your matrix A and multiply it by that vector. 1, 1, 1. That's what part C said to do.
Oh, that's the, okay, I see.
And so but the thing is, part C is giving me the intuition for part D, which is that, okay, I need to multiply A times a different vector and still get a multiple of that vector. Well, I'm just going to pick a multiple of this vector. So I'm going to pick something easy, like let's pick D equal to 3, 3, 3. So if you have a vector that has this special criteria where the matrix times the vector is equal to a multiple of that vector, then any other multiple of that vector will also have this special criteria. So A times D is going to be 7, 1, -2, -3, 3, 6, 2, 2, 2, multiplied by the vector 3, 3, 3. And if we multiply this out, let's see, we're going to get 21 plus 3 minus 6, which is 18. We're going to get -9 plus 9 plus 18. And we're going to get 6 plus 6 plus 6. And look, this is exactly a multiple of the vector D. It's also 6 times D. So that's what I'm pretty sure that problem was going for. They wanted you to use your observation from part C to then see how to do part D. Okay. Someone asked if I could please go over 28. Sure. Maybe. Let's see. 28. That's the way at the end here. There's 28 problems on this thing. Oh, sure. Yeah, 28. No worries. I might even give you an extra with 28 because I feel like this example is not personally my favorite, but it's a good example still. So, Leslie matrices. Consider the following model for the population size n sub t of an age-structured population with 2 age classes. So, and I feel like something is missing there, which I'm going to fix. Okay, sure. I'm going to write this the right way. It should really say n sub t plus 1 is equal to b times 2 times, or sorry, b2 1/2 0 times n sub t. So that's the idea, is you're saying the next year's iteration is this matrix times the previous year's iteration. And I would really think it might be easier to write this as, say, x sub t plus 1, bless you, y sub t plus 1 is equal to this matrix times x sub t, y sub t. And then the question says, for A, suppose that B is not equal to 0. Find all possible equilibria. Meaning, find n sub t so that when you multiply the matrix by n sub t, you get back the same matrix. Right? We've talked about equilibria before. They're the things that when you do a thing to it, they don't change. So multiplying the matrix by the equilibrium should give you back the same equilibrium. Okay, so we're trying to solve, let's just make it easier to write. We're trying to solve b2 1/2 0 times xy equal to xy. And so then my equation is going to be b times x plus 2 times y equals x, and 1/2 times x plus 0 times y equals y. Those are my equations, right? Just doing the matrix multiplication. This row with this column equals x. This row with this column equals y. Looking at the second equation, I see that y equals 1/2 x or x equals 2y. Okay, plugging that up into the first equation, I see that b times x plus 2 times y equals 2 times y. I guess I could have plugged it in over there as well, but I didn't. The two y's cancel, and we get b times x equal to 0. We've assumed that b is not 0. So if b times x equals 0, it can't be b, it's got to be x. So that means x has to be 0. And if x is equal to 2y, that means y also has to be 0. So in this situation, the only solution is the solution, or I should say the only equilibrium is 0, 0. So n sub t equal to 0, 0 is the only equilibrium. Which you could certainly check for yourself, right? If you plug it back in, this matrix, b2 1/2 0 multiplied by 0, 0, not surprisingly, is going to give us 0, 0. So it certainly is an equilibrium. You multiply the matrix by it, you got back the same thing. Okay, let's look at part B, where we're going to assume that b is equal to 0. And I'm going to give you another matrix that I think is more interesting. So suppose b is equal to 0. Well, then we're starting off with this 0 to 1/2 0 times the vector we're trying to find equal to the vector we're trying to find. It's the same sort of system of equations. We have 0 times x plus 2 times y equal to x, and 1/2 times x plus 0 times y equal to y. And you might notice that these two equations are really representing the same equation. Right? 2y equal to x is the same as, if you multiply both sides, 2y equal to x. So it means that as long as you satisfy the first equation, you satisfy the second equation. So actually here, there are an infinite number of equilibria. Any vector that lies along the line y equal to 1/2 x is an equilibrium. So for example, x equal to 2, y equal to 1. Or x equal to -6, y equal to -3. Or more generally, any k times the vector 2, 1. Let's see. Go ahead.
You're being animated. How is it like any vector that lies on the
Well, sure. So I want to point out that all of these vectors I just listed are solutions to both of these equations, right? If x is 2 and y is 1, then 2 times 1 equals 2, check. And 1/2 times 2 equals 1, check. Or if x is -6 and y is -3, 2 times -3 equals -6, check. 1/2 times -6 equals -3, check. So what I'm saying is any vector I should really say any vector whose terminal point lies on the line y equals 1/2 x is a vector that's a solution. Because basically we're just saying this line is full of solutions. So let's see it. If you take your matrix 0 to 1/2 0 and multiply it by any k times 2, 1 or 2k k, we're going to get, let's see, 0 times 2k plus 2 times k and 1/2 times 2k plus 0 times k. Oh, look, you multiplied the matrix by the vector and got back the same vector. That means it's an equilibrium. Yeah.
Is that because when you do x equals 2y, you plug it back into y equal to 2?
Right, exactly, yes. What I would say is it's really because these two equations are the same equation. They represent the same line. So here you have an instance of having essentially an infinite number of solutions because the two equations you have are two lines that are the same line. Whereas before, you only got one solution because the two lines were the lines that were not the same line, but crossed at the origin. So there was one point of intersection, and that point of intersection was the only solution. And then you can also have a system with no solutions if the lines happen to be parallel to each other. But again, that's something he tends to ignore as far as the exam, so we shouldn't delve too deeply into that. The other thing I want to point out is what if we had a different matrix? And I had one here, I wrote it down, and it's disappeared from my mind, it's all right. So let's say we have the same question, but now we wanted to say our n sub t plus 1 is equal to, oh gosh, I had it for a second. Why I wrote it down somewhere. Anyway. Sure. 2, 1, -4, -2 times n sub t. And I would like to find the equilibria. In fact, I want you all to find the equilibria. So I want you to do your best to solve this equation. 2, 1, -4, -2 times xy equal to xy. So it might be a little unsatisfying. It might be the same solution as before, but oh well. Sometimes you have the same solution as before. It might not be the same. Might only be 0, 0. That's happening. All right, let's see what we've got. So if I'm trying to find the solutions to this system of equations, I'm going to try to probably isolate a variable in one and then plug it into the other. So here, I'm going to subtract 2x from both sides and say y equals -x. And then I'm going to plug -x in for y over here and say -4x minus 2 times -x equals -x. And yeah, it looks like -x is going to have to be, or sorry, the x is going to have to end up being 0. You've got -4x plus 2x equals -x. You've got -2x equals -x. You've got 0 equal to x. So the only equilibrium here is 0, 0. And you know what? That happens a lot. So if x is 0, then y has to be 0. So in this case, the only solution is that 0, 0 is your only equilibrium. Sometimes that happens. Okay. So wouldn't x equal 1? X would not equal 1. So so if x were 1, let me actually, no, yeah. 2x plus y equals x. -4 minus 2. Yeah, that's right, yeah. If x were 1, then y would have to be -1 in this equation. But in the second equation, if x were 1 and y were -1, you would have -4 plus 2 equal to not what it needed to be equal to. So no, we don't need x. We don't get x equal to 1. We definitely get x equal to 0. And if x is 1 here, you get -2 equal to -1, which doesn't work. Yeah. Sure. Oh, changing it up. quarterback throws the football with an angle of elevation of 40 and a speed of 60. I'm guessing that's 60 feet per second. Sure. Someone's throwing a football at a speed of 60 feet per second, an angle of 40 degrees. Find the horizontal and vertical components of the velocity vector. So finding the x and y components really just boil down to using some trigonometry. So I'll remind everybody that sine is equal to the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So if we're trying to find the horizontal component here, we're going to say that cosine of 40 degrees is equal to the adjacent side divided by the hypotenuse, and the length of the hypotenuse is how fast the football was thrown, 60 feet per second. So I want to find the vertical component, sorry, the horizontal component, multiply both sides by 60, you get 60 times cosine of 40 degrees equal to x. So I would say that the horizontal component, x, is 60 times cosine of 40 degrees feet per second. Similarly, the y component, well, sine of 40 degrees is equal to y divided by 60. So y is going to equal 60 times sine of 40 degrees feet per second. This angle, so if it were asked this way on an exam, that's all you can do, right? Cosine of 40, cosine of 40, that's not an angle any of us are expected to know how to calculate. But if the angle was 30 degrees, then I think there is some expectation that you go one step further. So if my angle was 30 degrees, then we would get that x was equal to 60 times cosine of 30 degrees, 30 degrees, which is 60 times the square root of 3 over 2, or 30 root 3 feet per second. And y would be 60 times sine of 30 degrees, which is 60 times 1/2, so 30 feet per second. So if it's one of the well-known angles, 30 degrees, 45 degrees, 60 degrees, 90 degrees, there is an expectation that you actually evaluate them. Although, if you don't know, leave it as sine of 30, cosine 30, and move on. Yeah, go ahead. Mm-hmm.
Solving a differential equation that's both the first order linear and separable.
Sure, yeah. Yes, exactly, yeah. We've actually seen, so I would say one example, the kind of the prime example of differential equations like that are the tank problems where the volume and the volume out are the same. I'm gonna set it up that way just to kind of talk about it that way. So let's say we have tank that holds, I don't know, 100 gallons of salty water, and starting off with 30 pounds of salt. We're putting in some salt at, I don't know, a rate of 4 gallons per minute and a concentration of, let's not make it terrible, James, 3 pounds of salt per gallon. So that's the volume going in and the concentration of that volume. And then what's going out is we're taking it out at 4 gallons per minute. So if the volume in and the volume out are the same in these tank problems, which they should be if you're being asked to solve it, then it can be done either way. So let me show you. So first we're going to set up the differential equation. In fact, you all should take a minute to try to set up the differential equation right now. I'll help you out. The rate of change of salt should be the amount of salt going in minus the amount of salt going out. I'll help you even more. It's the concentration in times the rate in minus the concentration going out times the rate going out. Okay, I'll give you a minute. Right, times the wasted. So, bless you. DSDT here, the rate of change of salt. The concentration in is 3 pounds per gallon. The rate going in is 4 gallons per minute. So I'll point out that we have 12 pounds of salt per minute going in, a lot of salt. Out, the part out is always the part that's the most mentally challenging, right? The concentration out is the amount of salt in the tank, S of T pounds of salt, divided by the volume of the tank, which is 100 gallons, which is not changing because the volume going in and the volume going out is the same. And then we're multiplying that by the rate that it's going out at, which is 4 gallons per minute. So here's how we can set this up. We can write this as DSDT equal to 12 minus 4 times S over 100 reduces to S over 25. S of T or S. So here's our situation. And this problem can be done either separately or as a first order linear. So let me show you both ways. And I will say, when you have the choice, I actually think it's easier to do it algebraically as the first order linear. If you're given the choice, I would probably pick first order linear. I think it's going to be easier. So if we're going the separable route, the right-hand side, we have to kind of be able to separate, and there is no way to separate, so you kind of have to divide by the whole thing. Now, I would say the one thing to make this easier is to get the common denominator on the right-hand side. So we're going separable, rewrite ds dt as 12 times 25 over 25. 12 times 25 is 300 minus s over 25. And then I'm going to divide both sides by 300 minus s. I'm going to say 1 over 300 minus s ds equals 1 over 25 dt. Whereas, and we'll continue with this, but just to kind of show the contrast, if you're going first order linear, we're going to rewrite this equation as ds dt plus 1 over 25 times s equal to 12. And then you're going to find your integrating factor as mu of t equal to e to the integral of 1 over 25 dt, which is just e to the t over 25. You don't need the plus c or any of that other garbage when you're talking about the integrating factor. All right, so let's continue with this way first, because again, I think this is easier. So we're going to multiply everything in our equation by our integrating factor. So we have e to the t over 25. You might choose to rewrite ds dt as s prime at this point. So e to the t over 25 times s prime plus e to the t over 25 times 1 over 25 times s equal to 12 e to the t over 25. All right, if you're doing it this way, you should not, the next step should not require any thought. Don't think about this next step, just do it. Meaning, whatever you have over here, after you've multiplied by the integrating factor, you should always be able to write this left side as the derivative of the product integrating factor times s, or whatever your function name is, y, whatever. That is always, always, always how the left-hand side breaks down. And then the right-hand side still 12 e to the t over 25. And then you anti-differentiate both sides. So the left-hand side is e to the t over 25 times s equal to the integral of 12 e to the t over 25. Wow, my t's are looking real gross there. And then we integrate both sides. Sorry, we integrate the right-hand side. So you have e to the t over 25 times s equal to 12 e to the t over 25. And we have to divide by a 1 over 25 or multiply by a 25. Plus c. And then finally, our answer here is that s of t is equal to 12 times 25 is 300. So 300 e to the t over 25 plus c, all divided by, including the c, the e to the t over 25. And yeah, you could simplify that more, but I wouldn't. And then we could and should use the initial condition to, oh, sorry, you can't quite see that, apologies. We should use the initial condition to solve for c. On the other side of things, if we do it this way, we integrate both sides. The integral of 1 over 300 minus s is the natural log of the absolute value of 300 minus s with a minus sign in front equal to t over 25 plus c. We multiply both sides by negative. Well, oh, the negative is coming from the fact that there's a negative s right there, right? If you integrate, you have to divide by the coefficient of your variable here. So then we multiply both sides by -1, and we really just ignore the absolute value, even though it feels bad. So you get a negative t over 25, still plus c. You e both sides. You e to the natural log of 300 minus s. See how this is just, I feel like this is more terrible. You don't have to agree with me, but like, I think it's more terrible to do it this way. So if you have the choice, I would pick the right-hand side over here. And then e to the natural log of 300 minus s is just 300 minus s. And e to the negative t over 25 plus c is e to the negative t over 25 times e to the c, which just becomes a new constant. I call it a. And then solving for s, we get s equal to 300 minus a times e to the negative t over 25. Which is the same as that. It just looks slightly different because I didn't simplify this fully. But if you were to actually go ahead and divide through 300 e to the 25, 300 e to the t over 25 divided by e to the t over 25 is just 300. And c over e to the t over 25 is exactly some constant times e to the negative t over 25. So these answers are the same. They just look a tiny bit different. And then you would plug in p equal to 0 and s equal to 30, because we were told that there were 30 pounds of salt at the beginning of the process to solve for a or t. Question?
So for this one, it was only s over 25 because we had 4 gallons going in and 4 gallons going out, right?
Right. So up here, this part here is equal to 4 times s divided by 100, which is s over 25, because the volume going in and going out are the same.
And I know there's some problems where the volume is different, and that's when we would do the 1 minus the other times t on the bottom, right?
Correct. Yeah. So if you had like 7 gallons going in and 4 gallons going out, then the denominator would be, instead of just 100, it'd be 100 plus 3 times t, because you're adding 3 gallons every minute that you're doing this.
Okay, and then you would just have that variable t then.
Right. Right. But again, typically those problems we usually don't ask. Like you might be asked to set up a problem like that, but it is atypical to ask you to solve a problem like that. It's not impossible. It's certainly solvable, but then it would have to be first order linear. You could not solve it separately. Okay, someone asked about question 26. All right. So 26 is just another Leslie matrix. So going kind of the other direction. The following matrix represents a system of difference equations. When you see that, you should just think Leslie matrix. So here's the thing: 3, 0, 7, 9, 11, 0.1, 0.1, 0.8, 0, 0, 9, 0, 1, 1, 1, 6, 5, 4, 3, 2, and 0, 0, 0, 0, 0. Okay. So we're being asked to construct the diagram that goes with this. So how many categories do we have? 5 categories, because we got 5 rows and 5 columns. So I'm going to use A, B, C, and D because that's pretty typical. Sorry, and E, because there's 5, not 4. And I have to remind myself, so the first row are the things that are going into the first category. So 3, and then the things in the first, second, third, fourth, fifth columns are the things that are coming out of those respective categories. So into A is 3 times A, 0 times B, 7 times C, 9 times D, 11 times E. Going into B is 0.1 times A, 0.1 times B, 0.8 times C, and nothing from D and E. Going into C. So a complicated diagram here. Got 9A, use the A there, 0B, 1C, 1D, 1E. Finally, going into D, you've got some of everything. You got, wow, okay. So you got 6A, 5B. Sorry, I'm gonna have to cross some lines here. It's terrible. 4C, 3D, and 2E. And nothing is going into E. So it's that's a bit much for a diagram, but the idea still makes sense. So again, the rows are the numbers that are going into that category. So this is what's going into A. This is what's coming out of C. Rows are what's going into, columns are what's coming out of that thing. That is probably the easiest way for me to imagine it myself. Not just explain it. It's the easiest way for me to think about it. Like there's no better way I can imagine it really. All right, that's all there is to 26, I think, right? Yep. Okay. What else we got on the agenda? Yeah. Probably. Let's see. So I will point out, I think 23 is one of the ones he said that was for the final, but yeah, let's avoid 20. Yeah, oh yeah.
20.
Yeah.
What about 21?
What about 21? Sure. And then number 1. Okay, I feel like oh, there was one. Oh no, that's right. Yeah.
It's not titled.
So here's 21. I'm gonna ask 2 questions in 21. So the first question is find a vector that has the same direction as 2, 4, 2, but length 6. So here's how we do that. First, you're going to normalize it, meaning you're going to divide it by the magnitude. If you have a vector and they haven't given it a name, I find it convenient to have a name. So I'm going to call it whatever I want. I'm going to call it V. And it's perfectly fine to do this. So then the unit vector in the same direction is V divided by its own magnitude, which, oh, I hate this notation, by the way. I'm going to write it like this, 2, 4, 2, divided by the square root of 2 squared plus 4 squared plus 2 squared. 2 squared, which is equal to 1 over the square root of 4 plus 16 plus 4 times the vector 2, 4, 2. So this vector, I will point out, points in the same direction with a length of 1. Now I want a vector that points still in the same direction with a length of 6. By the way, if you multiply a vector by a scalar, a real number, it either points in the same direction if that scalar is positive or the opposite direction if that scalar is negative. So I need to multiply this vector by 6. So if I do 6 times the thing I just found, which is going to be 6 over root 24 times 2, 4, 2, that vector points in the same direction as V, and its magnitude is 6, or its length is 6. Two more things about this. What if I said we wanted to point in the opposite direction and have a length of 3? Right, you multiply by -3 instead. So opposite direction, length 3, you would do -3 times V over the magnitude of V. So whenever you find a vector of a certain length in a certain direction, take the original vector, normalize it, meaning make it length 1, and then multiply it by whatever length you actually need it to be. And then I'll add on here. What if I wanted a vector perpendicular to V? Well, there's lots of answers. Here's the answer I would pick. Well, one of them. So V is 2, 4, 2. If it's a 3-coordinate vector, make one of the coordinates 0. So my perpendicular vector here, I'm going to make it be 0, 1, -2. The way I picked that was just thinking of things that I could multiply by 4 and 2 to add it to 0. So if you look at the dot product here, V dot W is 2 times 0 plus 4 times 1 plus 2 times -2, which is 0 plus 4 minus 4, which is 0, which means the vectors are perpendicular, right? It's that literal definition of being perpendicular, is that the dot product has to equal 0. And then if I wanted the vector perpendicular to have a length of something, I would normalize it and then multiply it by its own length. Yeah. Boxes was so you would ask about number 1, but number 1's not on the agenda. Someone else is asking about number 12. About number 12. Okay, yes. We'll get to number 12, but go ahead. What was your question?
When is it parallel? Like what has to be true about that?
But two vectors are parallel? Two vectors are parallel. So these vectors here are all parallel because they're all multiples of each other. So the answer is vectors are parallel if they point in the same direction. Meaning they're just, the thing is, you can draw vectors, you can draw the same vector emanating from any point you want. So all of these vectors that I'm drawing right now are parallel, but they're all really the same vector because they're just starting in different places. So parallel vectors are multiples of each other. So V, 6 times V, 21 times V, -2 times V, all of those are parallel. So let's look at number 12. Another Leslie matrix problem here. So assume that the population, I'm just going to read this because the writing is terrible. So assume that the population is divided into 4 age classes. Yeah, I don't love using numbers so much. So let's say that our age classes are 0, 1, 2, and 3. Sure. Terrible. Yeah, I don't love this. So assume the population is divided into 4 age classes. Let's be smart about this, James. Let's just use A, B, C, and D. Here's our 4 age classes. A being the youngest, D being the oldest. So assume that the population is divided into 4 age classes. 70% of the females age 0, 50% of the age 1, and 10% of the female. Oh gosh, I have to read this more. So I'm exhibiting a bad example of reading the question too fast. I need to slow down because I need to understand what's going on. Assume that a population is divided into 4 age classes and 70% of the females age 0, 50% of the females age 1, and 10% of the females age 2 survive until the end of the next breeding season, meaning they all bump up to the next age category. So if I would draw the picture before I tried to draw the matrix. I keep saying draw the matrix. That's still weird. It's not a thing I would normally say, but here we are. So 70% of the age 0s make it to the next grouping. So from A to B is going to be 0.7. 50% of the age 1s make it to the next grouping. And 10% of the age 2s make it to the next grouping. Okay. Further, the females age 2 have an average of 4.6 female offspring, and the females age 3 have an average of 3.7 female offspring. So the 0, 1, 2, the age 2s have an average of 4.6 age 0s, and the age 3s have an average of, I forgot what the number was, 3.7 age 0s. And I think that's it as far as the matrix is concerned. Okay, so let's let's find the Leslie matrix. So row 1 is what's going into A. So we have none of A itself, none of B, but 4.6 times C and 3.7 times D. Row 2 is what's going into B. So we have 0.7 times A and nothing else. Row 3 is what's going into C. We have 0.5 times B and nothing else. Finally, row 4 is what's going into D. We have 0.1 times C and nothing else. And this is a pretty standard look for a Leslie matrix where like it's actually like a thing that is getting older, right? You have a top row of the new births, and then you have everything just one below the main diagonal having non-zero elements, and everything else is 0. And then the question says, if at time t equals 0, the population consists of, for time equals 0, we have 1500 age 0, we have 500 age 1, we have 250 H2, and we have 50 H3, then find the Leslie matrix, which we just did. That's our Leslie matrix there. And the age distribution at time 2. So essentially, we want to find, if I call this x naught, we want to find a squared times x naught. We want to do 2 iterations of this process to see what we get in 2 years. So the way I would do this is, sorry, I wrote a squared. I should have written L squared because they called it L. Sorry about that. Should be finding L squared times x naught. So I'm going to do L times x naught. And that's going to be equal to, well, first here's L times x naught. It's the matrix up there. Writing out the matrix is kind of tedious sometimes. Before I forget, just so everyone knows, I know I didn't say it today, but I think it's the last time. A transpose matrix, you just change the rows and columns. So if I was finding the transpose of this matrix, this first row would become the first column. This second row would become the second column. Third row would become the third column. Fourth row would become the fourth column. Transpose matrix is super easy to write down. You're just literally changing the rows and the columns and the columns and the rows.
And did they say anything about like how you can't like multiplying matrices not like
It's not commutative.
right? So if that was the case, why can you do L times x naught before you do L times L?
Well, so matrix multiplication is not commutative, but it is associative. So here's what we can't do is we can't say, right, L times x naught. I can either do like this or like this. Because I'm not changing the order of multiplication, right? It's not the same as L times x naught times L. Right? We can't change the left-rightness of the multiplication, but we can change the groupings together. So in what the difference here is the difference between saying like in regular numbers, it's solely cool 3 times 2 equals 2 times 3. In matrices, A times B does not equal B times A. But in regular numbers like 3 times 2 times 5, you would calculate that either by doing 3 times 2 first and then times 5 and getting 6 times 5, which is 30, or doing 3 times 2 times 5 first, which is 3 times 10, which is also 30. That property does work for matrices, meaning you can group whichever two you need to multiply first together. So, and again, I'm always going to try to do the matrix times the vector because it's usually easier. So doing that here, sorry, I've written it up here. Let's kind of, I know it's 10:23. If you got to go, you got to go. We'll finish this example and then I will stop talking. So L times x naught, which I was writing up there and then kind of ran out of room. Here's the matrix. We're going to multiply this by the initial population vector, which is 1500, 500, 250, 50. I should also mention, I did post a handout on Leslie matrices with solutions as well. I think it's well worth looking at if you have more questions about Leslie matrices. Here we're going to get 0 times 1500 plus 0 times 500 plus 4.6 times 250, which is something, and then 3.7 times 50. So 4.6 times 250 plus 3.7 times 50. And then we get in the second row, we have 0.7 times 1500, which is going to be, I think, 1050. And then in the third row, 0.5 times 500, which is 250. And then in the fourth row, 0.1 times 250, which is 25. And then you do it again. So then L squared times x naught is just going to be L times the thing we just found, which is going to be the matrix 0, 0, 4.6, 3.7, 0.7, 0, 0, 0, 0, 0.5, 0, 0, 0, 0.10, multiplied by that right there. Grant's going to start coming in here in a second. So then you would do it again. You would say this row dotted with that, this with that, this with that, this with that. All right, I'll have office hours over in C class. shortly, and then over in drop-in this afternoon. And then tomorrow morning in the usual spot from 10 to noon, essentially. All right. Study hard, do your best. Got questions, don't hesitate to come see me. Or other folks.
Anything about.
Tamara Galiaba, is she teaching 17C? Oh, she's teaching it right now, yeah. I mean, she's fine. She gives a lot of practice tests. Her tests always feel like they're just a little bit harder than the practice test she gives. Like she usually just twists one problem a little bit. But I mean, she's all right.
No, we're taking her right now, so we're.
Oh.
we're final.
Oh, okay, sure. I mean, so you've had 2 tests with her. You can, I mean, as far, I would say, as much as your actual exams have been similar / dissimilar to your practice exams, I would say you can expect the same thing for your final. It'll be similar-ish, but not quite the same. Definitely do the practice exams is my best piece of advice for her. Yeah,
But thank you.
you're welcome.
That's good.
You too.